My name is Peter. I really hope for internet the, the internet connection will be stable because I have like 80 slides. All of them are images or videos, and I just plan to just voice over them. So yeah, I might ask you to, in the style of Steve Jobs, kind of like get off the Wi-Fi for the remaining 59 minutes of this presentation, if that's okay with you. Oh, there's my phone. Cool. Okay, so let's start. Like I said, my name is Peter. I am open source lead at RoboFlow. We are a US-based computer vision startup. We build tools for enterprises, but also for like individual developers to take their computer vision project kind of like from the idea to the production. And we have all sorts of tools to help you do that, to annotate the data, to train the models, to kind of like we also have like a low code tool to build um, AI applications around that model and to take that model to production, whether it's cloud or edge device that's on your forehead. We probably can do that. So that's who we are. We also are pretty active in open source space. We maintain several open source computer vision projects. Um, Collectively, they have around 80,000 stars on GitHub right now. And my job is, in large part, uh, coming up with new projects and maintaining them. That's a big part of what I do on a daily basis. Big test for first video to play. Cool. Okay. So I also build demos, and I also build like tutorials to help people to understand how to leverage computer vision to solve like everyday problems, focusing on like open source models. So this is like a example of what I do. Yeah. So here's a road with cars. We detect the cars, we track them, we estimate their speed based on distance from the camera and visualize them on like a virtual road. Yeah. So that's an example. Um, I'm also a big sports fan. So I used to play basketball. I will totally not play one-on-one basketball with anybody today because I have a wedding in 2 weeks and I need to stay away from injuries. And that's totally the only reason why I'm scared to play basketball in Lithuania. Um, but yeah, I decided at some point it would be cool to use sports as a playground for like building those demos. Sports is very weird, yeah, because small changes, small differences can lead to like big outcome changes, like a fraction of a second or a centimeter left and right, and you can win or lose games. For those basketball fans here, maybe you remember like Kevin Durant shoot like a 3-pointer in Game 7 of playoffs when he was in Brooklyn Nets. Turned out his toe was like literally 1 centimeter on the 3-point line, and it was 2-point shot, not the 3-point shot. They didn't want that serious. Spoiler alert. So that's why we use sports as a playground for testing computer vision models, because if they perform well in sports, there is a high chance they will perform well when you solve like other tasks, because usually they are less demanding. So the whole project that I will cover today is open source. The code is open source. The models that we use are open source. So you can scan it, you can play with it. It will lead you to Google Colab. You can run it for free on their GPUs if you have like Gmail account on the free tier. Okay, let's take a first deeper look into this project. What is inside? We'll dive super deep in those 45 minutes or an hour. So there's a computer vision model for object detection. We detect 10 different classes, and it powers a lot of the features that are in this project. There is tracking, and basketball tracking is actually pretty hard to do. Because people overlap each other very often. It's like if you think about volleyball, for example, everybody's spread out. It's like teams are on the other side of the court. With basketball, when you have rebound, for example, everybody gathers under the basket. And obviously, people are setting screens for each other. So there is like a lot of movement and a lot of occlusion. So tracking is notoriously hard in basketball. I will also show you how to divide players into teams based on how they look. And we'll also try to understand where is the court. And as we will understand where is the court, it will help us to calculate more advanced metrics and extract more advanced information. So we'll be able to say who is where. We'll be able to say where they took a shot and map that shot on the map of the court. And we'll of course be able to figure out the whole trajectory of movement. It's important to say that we are not like sports analytics company. We are totally not. We are a general computer vision company. We just do it for like lols pretty much. So yeah, to disrupt space and to give people tools to build it on their own. That's pretty much what we do. Okay, cool. So like I said, we need to start with object detection. So anybody who did object detection here over the past few years, I assume you used YOLO. That's what people used, I hope. So YOLO is like a model. The first YOLO model was released like 10 years ago. And YOLO stands for you only look once, just a side note. And the name is telling because before YOLO, people were using in most cases like a two-stage detectors. So there was like part of the detector that was coming up with ideas for where the object could be. So it was like generating 100 or 300 potential boxes where boxes where the object you look for could be. There was the other part that was like kind of like classifying those boxes. So I was like looking at each of those boxes and say, that looks like a person. Oh, that doesn't look like a person. Yeah. So you get like potential outcomes and then a mechanism that attached the class and the confidence for that class. That's more or less how it worked. And now YOLO changed that because it was processing everything in like a single swoop, so it was way faster. Yeah. But to be honest with you, the whole kind of like object detection research kind of stagnated for a few years now. We are at like YOLO 26 at this point, and most of the time they just kind of like beat the previous model by like fraction of MAP. This is the metric we use in object detection. Fraction of MAP means like they probably overfitted the model more than the others, and that's how they beat them. Yeah. So that was the case. And now, a few years ago, transformers, you probably heard about them, started to be important. Mostly in language, but because how language works and how image processing works, it's actually you can actually use transformers to process images as well. But and probably like a year ago, 2 years ago, transformers started to be more accurate than convolutional neural networks because YOLO is a convnet. They were way slower. But yeah, we released a model last year called RFDETR, is a detection transformer, and we finally made it fast enough that it's actually more like it's actually faster and more accurate than YOLO models. So we are in this stage right now where where transformers are probably better choice than convnets if you do object detection. Generally speaking, you would like to be here. Like that's the most optimal. Like that means that you are super fast and super accurate. And importantly, we made those like super small models called nano models, like 10 MAP faster at the same speed, which allows you to run them, for example, on mobile devices and still get really good accuracy. Okay. Important thing about this chart is that it is this MS COCO benchmark. So MS COCO is like a data set released by MS, Microsoft, 2018, I believe so. But they collected data for a few years in collaboration with other enterprises. I believe Meta was also involved. A bunch of universities, they collected the data, they annotated that. Problem with that, this is the subset of images from that data set. Like a part of this guy, and I really didn't cherry pick. I scrolled the Coco dataset for 3 minutes, literally, and that was it. There's also like a lot of public toilet images for some reason, which is strange because public toilet is not one of the classes that is in Coco dataset, so I'm not sure why. But a part of that, totally unhinged images in that dataset. Yeah, you can think about how the world looked like in 2018. those images were released in 2018. They were collected for several years. So let's say 2015. Like it was completely different world, especially if we talk about like tech. Yeah. So this was the phone in the dataset. So you can imagine that if you show somebody this, they might not recognize it. But at the same time, if you show this model that is pre-trained on Coco dataset, your phone, it also might not recognize it because it looks differently. Very often they like say it's remote controller or something like this. Screens look differently. Sorry, screen. What the, okay. Screens look differently, and computers look differently. But also, this dataset does not have like images of medical images. It also doesn't have like drone images. In 2015, almost nobody had drones. Who had drones in 2015? Like right now, almost half of 14-year-old children have drones because they got it for Christmas or something like this. So processing drone data was not very popular back then when this data set was released, and now it's very popular. So that creates a problem because when you fine-tune YOLO models on custom data sets, very often they don't learn very fast because they don't have that knowledge. They only were pre-trained on Coco datasets, so they don't know how to like grow from that knowledge pool. Yeah. Whereas RFDTR is based on DynoV2, it's a model from Meta. It was pre-trained on like massive data set, very diverse, like medical images, drone images, all sorts of stuff was there. So it has a lot more knowledge. So it's very common that after 3 epochs of training RFDTR, we get to the level that YOLO needs like 70 epochs to train, pretty much. And this is an example of like a project that I built with RFDTR, just fine-tuned it on open source Visdrone dataset and just created this. And I trained YOLO models on the same dataset, and they got like 10 MAP less on the same use case. I promise this is the last like unrelated to basketball slide here. So we also took RFDTR and benchmarked it across more aerial datasets. So not only Visdrone, but also other datasets. And on average, if you fine-tune YOLO, top YOLO models versus RFDTR, you get between 2 and 5 MAP points difference, just by the fact that you just use this model and not the other. You train exactly the same epoch count, the same batch sizes, the same, everything is the same. So it's a pretty good choice if you would like to fine-tune your model for custom task. Yeah, we are in basketball once again. So this is our data set. So what we did is we kind of collected 20 games. We took 10 plays from each game and we annotated them with multiple classes. So we have classes for player and for number. I will show you why we have them in just a second. We also have kind of like more detailed classes for player. So a default one is player. If he's just hanging around, like doing nothing, hanging in the corner, he's player. But if he is in possession of the ball, he's player in possession. If he is shooting a layup, he has a class. If he is shooting a jump shot, he has a class. If he plays active defense as blocking the shot, he has the class. We also know where the rim is, we know where the ball is, and we know when the ball is in the basket. You probably know why we would like to know that. And this is kind of like the demo, should be, okay, for that. A lot of blinking, I know, but we'll just pass for a second so that you can see what's happening. So player in possession, the ball, we know where all the players are. There's also referee class because we would like to know who is referee and who is player. There's that. Also notice that there are players over here that are not annotated, and the model kind of like learns on its own that that's not the player that is interesting to us. We only care about the players that are on the court. And we'll just let it play to the end. You will see this play a lot because most of my visualization is for like the same play because you can then do pretty cool stuff. I told you that this is the last RFDTR slide. It's not because it's also segmentation model. So if you would like to have more information, because bounding box gives you information about what is where, but segmentation gives you what is where and exactly where, because you can segment that. So it's also state-of-the-art segmentation model right now, the fastest and the more accurate. And if you would like to play with RFDTR, here's the QR code. I highly encourage you guys to scan it and give it me star, because my kind of like bonus, end of the year bonus, is based on stars. So if all of you will star, it brings me closer to my bonus, and that's great. So I leave it for a few seconds so you guys can do it. Okay, cool. Cool. So we detected the players. Now we need to track them. So here is a different demo that I did 3 years ago. That was done for football, and once again, very small numbers. But what you can see is, if you will focus your attention, for example, on this group of players, you will see the amount of numbers that they will get. So if everything works correctly, they should have the same number all the way. But they don't. That guy was 43, now it's 47. You know, stuff happens over here. Why is that happening? Because those trackers are based only on like bounding boxes. So we have detection. We run detection across all the frames, and there are two players that one of them has ID 1, one of them has ID 2, and they are on trajectories that will collide. Yeah, and when they collide, for a fraction of a second, what happens, one of them is not visible, and you only get one box. So the tracker gets confused, because when it's only get one box, it will attach that box to one of the tracks, but the other track has no bounding boxes to be still alive, so it dies, and then the player reappears. We don't have a tracker in that area to attach that, so it reemerges as new tracker ID. So that was 3 years ago. I was a lot worse at tracking back then, but also there was a lot less options. So this is segment anything free, a model released by Meta, third iteration, and what it can do tracking. It can do tracking the video. It do kind of like a mix of segmentation and tracking, and you can also prompt it. You can prompt it with text. So, for example, for that demo, I was just saying jets, and it was giving me the jets, yeah. And then I was say, hey, skier. All I did is give it the video and the text, and it did this, yeah. Cars. Cool. Here is interesting concept, because I was trying this also on basketball, like on its own. It requires a little bit of creative prompt engineering. You can see that I use prompt active player. This is because I wanted to exclude those guys here. And if you use player, Boston Celtics player, you can even get this guy if you ask for Boston Celtics players. So yeah, a little bit of creative prompting here. But yeah, it works. Now, what you can also do is you can prompt segment anything free with boxes. So instead of saying player, you can say, hey, those guys. So this is the first frame of the video, yeah? And we run detection model on the first frame of the video and say, hey, I would like to track those guys across the video. You can give the model the boxes, give the model the sequence of frames, and what it will produce is pretty much this. So very good, high quality tracking data from that play. And the only downside is very slow. It's like its speed is like real time if you track one object, but it goes linearly down with every object. So it's twice as slow with 2 players. It's 4 times as slow with 4 players. You get the point. But they released segment anything 3.1. I didn't test that yet, but the benchmarks say it's like 10 times faster right now when processing video. So I might test it at some point to take a look. There's also one more thing that is a little bit inconvenient with that. So let's pass here. Okay, so the problem is that when we prompted that model, this guy had the ball. And the model thinks that ball is like a part of that person right now. Yeah. So if you shoot the ball or pass the ball, which generally speaking you do a lot in basketball, then that ball is still associated with that player. You can see that the bounding box is still like this. That wouldn't be a problem, but we try to build more advanced analytics based on that, and errors like this will just compound, and with every model that you will stack in that pipeline, that problem will just grow. So we need to use a little bit of like old school computer vision, like opening and closing operations from OpenCV. Maybe some of you did something like this. It's very fast. Generally allows you to, like, there are ways in OpenCV to just look for clusters of pixels and say if the centroids of those clusters are far enough from each other, etc. Then you can filter it out. So that's what we did. You clean that data and we have like a better quality. So there's that. And also I have segment anything free tutorial if you would like to play with like tracking objects on the video with text or with boxes. Will also lead you to totally free Google Colab that you can just open and run for free if you have Gmail account. So yeah, have fun. Cool. And that project, football project that I did some time ago. Jesus. Yeah, my kind of like pride got hurt, so I became kind of passionate about tracking, and I'm building open source project just for tracking, just to make tracking as good as possible. And this is like one of the demos we made quite recently. So yeah, it's way better now, way better now, but still less accurate than segment anything. And for the basketball AI, we really needed high quality tracking data. Okay. And yeah, more like I will just spam you with QR codes. If anything is interesting, you can just find it. Cool. So now what we have detection and we have tracking. And we would like to get more information about those players. So we would like to know who they are. The first step to know who they are is to be able to say for which team they play. So you saw this slide already. We have the detector that can detect players and detect numbers. What we can do then is we can crop out those players from the whole frame. We also kind of like crop out like a specific part of the bounding box, like based on some heuristic to just limit the amount of noise. Because you can think like if I will just stand like this, which is very common posture in basketball, and I will have bounding box around me, there will be tons of things in my background if I stand like this. So we just limit the amount of like attention that we give to the background by just picking part of the bounding box that have information about the actual player. And what we did is we used embeddings. So what we did is we ran embeddings model on each crop for the player. So you probably know what are embeddings, but generally, in case of images, you can run embeddings model. It will produce like a vector, and that vector kind of like describes that image in some high dimensional space. The first one was probably Clip from OpenAI when OpenAI was still open. And it allows you to also vectorize the text. So you can vectorize the text, vectorize the image. You get those vectors and you can use cosine similarity to compare text with images. You can do that. I didn't use Clip, but I used Siglip, which is, I believe, DeepMind's open version of Clip, where they also show people how they trained it. But the idea is the same. So what I end up is just kind of like, it's just a visualization because this is like 300 plus dimensional space over here. But I'm ending up with like a high dimensional space of points where each point is connected to a cluster. I use a technique called UMAP. You might use like TSNE or UMAP. It's like a library that allows you to go from high dimensional space to less dimensions. So you can have, theoretically speaking, like the same amount of information, but within a smaller dimensional space. And then I used like clustering algorithms, k-means, I believe so, to cluster those vectors into two groups. So I got two teams. Yeah. So, and each of those points is associated with the crop, so I know who is playing for what team. I mean, I know who is playing for the same team, pretty much. I don't know what team is that, but it is what it is. So this is the outcome. So you remember we had this, and now we can get this, yeah, just by using this trick. I do it only for the first frame of each play. because then I attach that information to tracker ID and some free propagates it through the video. So I don't need to do it for all the frames. And this is the outcome. So now we can say we have team blue and team green, and we know who is playing with who. And like 3 weeks after I made this, new model came out. That was Quen 3 VL. Now we have Quen 3.5 VL, but that was Quen 3. It is pretty cool because it allows you to build a completely alternative pipeline to what I just showed you. We can just straight up prompt the model, take the first frame and say, hey, give me players in white, and it will give you all the players in white. Christoph Porzingis here. And you can also say, hey, give me New York Knicks players. And it knows how New York Knicks look like. So it has that information and it can give you this. So what you can do is now you can say, take the first frame, prompt Quen twice for give me basketball players from Boston Celtics, give me basketball players from New York Knicks. Then you take that, associate that with your tracker IDs and just segment anything free through the video and it will do the magic. Yeah, you can also do other things with this model. You can say give me player number 7, which is a little bit foreshadowing because we'll talk about reading jersey numbers in just a second. You can also say give me a player that is about to shoot, or give me players that are sitting on the bench and they are New York Knicks. And this is interesting because that gives you this flexibility. We have the detection model that can detect only players on the court, but there are situations where you would like to maybe detect players that are sitting on the bench. I don't know, there are playoffs. There is LeBron James. You would like to have camera on LeBron James all the time. So you'd like to use computer vision to automatically point the camera at him. But when he's on the court, you see him all the time. When he's sitting on the bench, you can no longer detect him. So now you can. Yeah, now you can expand and be more flexible by just prompting, which is pretty cool. And I was just goofing around with that model to look for other things. I don't know, give me sponsors logos, and it was capable of doing that. Yeah, if you want to play with Quen 3 VL, I have free tutorial for this as well, so you can do it. Okay, so now let's talk about digits, reading the numbers from the jerseys. So this slide, you already know, we can detect players, we can detect digits. You can also crop out because you see that we cropped out the players, so we can crop out the image. This is the digit, yeah. So it's a very blurry digit. What can it be? It can be 0, it can be 9, it can be 8. It's 8 actually. If you will watch it through the game, then it's clearly an 8, yeah. But if you will see like just a specific frame, it's actually not that easy. Yeah? So this can be what? This can be 5, this can be 3, this can be 9, it can be 8. It's actually 9. Yeah. This is obviously 0, yeah. So it's actually 10. So so the purpose of this whole exercise here, what the heck just happened? Okay, the purpose of this whole exercise here is to tell you that if you look at just one frame and you will just run OCR model, object character recognition model, on one frame, you will not find out who that player is. That's for sure. So we need an OCR model that can run fast because we need to run it more than once for players. Generally speaking, we would like to run it every 10 frames, every 24 frames. You get the point. Like on regular intervals, we would like to run that model to kind of like yet another data point for us to know. So I was using small VLM2. It's a model developed by Hugging Face, also on Apache 2 license. But since then, there is a new model called GLM OCR, and it's way better. So here is an example. So this is like an OCR model, but you can prompt it with text. So for example, I don't have the image here, but generally you see there is a timestamp here on those images. So if you will run it by default, it will read all the text on the image. So it will read the license plate, it will read the timestamp, but then you can say, hey, give me just the license plate, and it gives you the license plate. It's pretty cool because it has like less than a billion parameters, so it's small enough you can run it almost real time on your local laptop, and it's very accurate. So it's exactly what we are looking for this project, because we can run it multiple times for those players and don't get punished for being super slow, or don't get punished because you need to call Gemini API to extract that information. So here is demo with license plates. Here's the demo with tire serial numbers. I'm not sure if you know, but your tires have serial numbers. Very hard task to solve, to be honest with you. Damage, dirt, weird location, like distortions, all sorts of things. It can read that almost perfectly. Yeah, and just like one more example of like being able to read dates from timestamps, from post stamps. Sorry, in US you have like 20 different kinds of post stamps for some reason, I don't know. So reading text from them and being able to process that is pretty cool. Okay, so this is a video where I will show you how it works. So what we do is we detect those numbers. We run like a regular tracking to know that this number is belonging to, like, this is the same number as we saw before. And then I will just maybe pause it at some point so you will kind of like be able to see what's happening. And then we run this fast OCR model to get information about this. Yeah, so we can see that we have some data for those numbers that are more obvious, and we have less information for cases where it's less obvious. So for example, Al Horford, number 42, was not recognized before. Yeah, because just bore that, he was sideways to the camera. So we didn't have enough information to say for sure that it's Al Horford. But with time, when he was turning his back to the camera, we got enough data points to say it's Al Horford, number 42. So this is how it looks like. Cool. This is how it looks like with time. So you can see that there are some players that from the very beginning of that play were turned with the back to the camera. Number 2 was way more visible just a few frames before. Yeah, so they were with the back of the camera, so we could get that number like confirmed very quickly. And those players were not. And with time, if you will kind of like scroll through it, you will see that now we have number 2, number 8, 11, and so on and so on. And if we will just play it till the end of the video, and we'll see we got all of them at the end. Yeah. So now we know what is the team they play for, and we know the number they have. So that's pretty easy. NBA allows you to just grab the roster for the team for a given game over the API. You know the team, you know the number, you know the player. So now we know if you would like to play with GLM OCR, free tutorial. So feel free to scan it and save the link. So now we know who is playing, but we don't know where they are. So to solve that, we'll use the same approach from applications that you use for scanning documents. Yeah? So if you scan the documents, you have the piece of paper on the desk, you pull up the phone and you scan it. It really asks you to put all the corners of that paper in the frame. Or if it's smart enough, it kind of like knows where the edges are, so it kind of like figures out where the corner would be. There is a reason for that, because it needs 4 reference points to perform homography. So this is kind of like a old school way to de-warp perspective, and you need at least 4 points to perform it, to calculate so-called homography matrix that allows you to go from one perspective to another perspective. And because if you watch game of football or basketball, you know that the camera moves constantly, pans and zooms. We can not only have 4 reference points, because there is a high chance that if it will just focus on like this half of the court and we would just have corners of the court, we actually only see one corner. Yeah? So what we need to do is we need to have enough points so that there is a high probability that regardless of the camera perspective, we would have all of those points in frames. So we picked 42 points on the court. It was by far the most time-consuming part of this whole project to annotate all of those points on like 700 images, but we did it. And the dataset is also free to use and open source. So if you would like to build something on top of that, you can do that. And now what we can do is we can perform the homography. Okay, I will show you the results. So we trained the model that was capable of detecting those points so that when the camera moves, those points kind of like are recognized. We know where they are on the reference frame. We obviously know where they are on the court, yeah, because basketball court has predefined dimensions, different for FIBA, different for NBA, but generally speaking, predefined dimensions. So we know where they are in the real life. This is our like target perspective, like top-down view on the court, and this is our camera perspective, and we also know where they are in this perspective. So we can compute the homography matrix, and we can transform the coordinates from one perspective to another, which allows us, give me a second, 73. Okay. This is what I meant by I added some slides at the last moment. That should be after that slide. So this allows us to map the position of the players from the perspective of the camera onto the court. So we can do this. And it all works until somebody jumps. Because of how homography matrix is calculated, the assumption is that all the points are on the same plane. So they're standing and their feet are on the same plane. This is the court. But the moment they jump, they're no longer, which is a problem. And now what I wanted to show you is, the visualization of that problem. So here is a case where I just highlighted one of the players over here. He will get the ball and shoot the ball. You saw that play many times already. So he is, first of all, he's going like he's for a second occluded by the referee. This also messed it up a little bit. So he's going, and when he's occluded, you can see that his trajectory is no longer linear, even though that he's most likely moving linearly. And then when he jumps, this is what we get. Yeah. So this would be the final kind of trajectory that we get from it. We would be able to do way better job if we have more than one camera, generally speaking. But you can still do better. Yeah. So this is the trajectory you get, like the raw trajectory you get from this setup. You can do a little bit of like a signal processing. So something that you do in old school time series processing, where you say, let's just make sure that the time series that does not move between two data points by too much and so on. You can identify the moments where the movement is just too rapid to be realistic. Because if that would be the chord, that would mean that the guy literally teleported in like fraction of the second by 3 meters or something like this. And you can just kind of like make it just a little bit smoother. Still not perfect, but because like I said, you would need to have more than one camera, but you can fight this problem. Sorry. And this is the final outcome that we get if you apply all of the smoothing and all of the processing to limit the amount of noise in that data. And because now we know who is where, and we also maybe remember are capable of detecting players that shoot the ball, and we also are capable of detecting when the ball is in the basket, we can now compute things like this. We can now chart the shots being made or missed, and we can even calculate the distance, yeah, because we are operating in that space. We already know where he was in real life. We know where the basket is, so it's not a problem for us to calculate the distance from the basket when he was shooting the ball. And this is pretty cool. ESPN, I guess, used that. So if you watch basketball through NBA app, sometimes they show you like if Steph Curry was shooting the ball from like 30 feet, then they visualize that somehow. This is pretty much how they do that. Yeah, you can do it with open source models and free Google Colab subscription if you want. Cool. Now, can AI be referee? So that was the area where I was like, okay, let's just try to do something. And so those of you who know basketball, you know that there is something called 3-second violation. For those of you who don't know, it's like a stupid rule that NBA never enforced because referees just are too busy doing other things. Generally speaking, you cannot be here for more than 3 seconds. Unless, and there is like a whole list of things that you like that would kind of like make you immune to that rule. Like, for example, you are here for 3 seconds, but you intend to leave. So you are already on your way out. Yeah. So then you can be more. So essentially in NBA, there are players like Rudy Gobert who are just like camping over here and almost like spend half of the play over here and just prevent you from shooting layups. And it's also like if your 1 feet is outside of this area, then you are not in this area. But for example, if 2, then you are in this area. So it's very hard to build like a computer vision system to reliably be able to say whether or not you're in violation or not. But we tried, kind of succeeded. Porzingis is camping, guys. It's happening. And yeah, you can see it in slow motion as well. So we use pose estimation models. We know where the feet are. We know where the area is because we can also like take this 4 points and convert that with homography matrix to real dimensions. We can do all of that, yeah, because we already solved that math. So we can know that. Now, there are also those VLMs I told you about, so those transformers that are pretty cool because they can process videos and images at the same time. And there is a competition on, there's this conference called CVPR, the biggest computer vision conference. There's like each year there is a competition related to soccer, I mean football, but they call it SoccerNet. And this year, what was there is was like, can we teach the model to automatically say it was a foul or not? And if that was a foul, was it a red card or yellow card? And they gave you multiple perspective of the play, and you were supposed to train the model. Everybody trained VLMs because that's what you do in that case, and those models are already capable of doing that. So I think we already have VAR system, and we are very close, I think, to have like automated systems that would make us all angry and shout at the computer because they will make stupid mistakes. So yeah, that's is coming. So stay tuned for that. That's it. Yeah, I hope that you enjoyed the presentation. If you have questions, then I'm happy to take them.